So if we have a random variable that's distributed normally with some mu and some sigma squared, we came up with the mathematical description of its density. But in practice, we never use the density function directly. We always have an interest in calculating probabilities. And that means we need to calculate areas. So what we need is the CDF of this general normal density. So, for instance, if we are given a problem as such, where we say, here is my general normal curve, I would like to figure out the probability that x is less than some value. So I would like to know the chance that this random variable takes on values, everything up to and including this, so everything as a left area. So the CDF is what's used here. So by definition, the CDF is an antiderivative of our density function. And we don't ever specifically use the density function directly in terms of the details. It's always much more convenient for us to write everything in terms of a transformation of the standard normal density. All right, I should be careful here. Write this as a y. So we make a substitution, as always. Z is y minus mu over sigma. dz will be dy over sigma. The infinite limit will not change, but the upper limit will. And the upper limit will become x minus mu over sigma. This will get us phi of z dz. And the point of the story here is that this just ends up being the CDF of the standard normal at a different location. At the location x minus mu over sigma. This is a process that we're going to call standardization. The function transformation, where we say z is x minus mu over sigma, a general normal into a standard normal, and it will preserve areas. That's the important part here. So on the sheet that's attached here, the IQ problem, I'm going to try to show this to you as an example. So we are told that we've got a normal density. So we've got x representing IQ score. And we are told that x is normally distributed with a mean of mu and a variance of sigma squared. We're told that the mean is 100 and that the standard deviation, not the variance, the standard deviation of scores is 16. So the question that we are asked is, what's the probability that I'm going to encounter scores less than 115? Now note, because we're using a continuous random variable, it doesn't really matter if we talk about less than versus less than or equal to. So in terms of a picture, our general normal for this particular problem has some sort of illustration like this. And we are now interested in this area. So there are a couple of ways to solve a problem like this. Perform what's called a standardization. And we will say, let's define a new random variable, x minus mu over sigma. And this is going to convert our problem from a general normal into a standard normal. So here the axis is x, whereas on this other case, the axis is z. So x equals 115 tells us that z is going to be 115 minus 100 over 16. So it's 15 over 16, which is 0.9375. So what we have done is translated our problem from something to do with x scores, so general normal scores, into standard normal scores. And the beautiful thing about it is this function transformation that we described above preserves areas. All we can do is simply calculate this. We can use r and calculate this value. Now, be careful when using r, because r always wants this value to be the standard deviation, not the variance. So you just end up with some value, 0.8257493. This is an important conceptual way of handling normal problems. You take any problem and you essentially collapse it or distill it down to the standard normal. And that way, every problem becomes a standard normal problem. This is a conceptual tool that's very strong. In the old days, when you actually needed to calculate a value for these areas, everything had to be collapsed down to just one standard distribution so that we could concentrate our efforts on one normal. And so in the olden days, they used tables to calculate CDF values. But in modern days, we can just use R directly. If we want to calculate the probability that x is less than 115, there's no need, if a number is our goal, there's no need to do the standardization process. You can just use R directly to get the same number. But the standardization process isn't so much of a calculational tool, but a conceptual tool. And later on in the semester, we're going to use this standardization idea to come up with other distributions that will help us.